Okay, so today we'll solve Gate 2023 questions from functional analysis. Basically, today we'll solve only two questions, 32, question number 32 and question number 37 from Gate 2023 MA. Okay, let me play the video for question number 32. If you have any doubt, you can ask. Okay, so today we'll solve mathematics Gate 2023 question. This is a question from functional analysis. This is a question number 32. It is saying that let L of minus 1 comma 1. So this is basically all square integral function where the functions are Lebesgue measurable. Right, so this f is a function of minus 1 to 1 to r. F is Lebesgue measurable and the function should be square integral in minus 1 to 1. With the norm, because this is finite, then you will take this quantity to the power half. Then this will become a norm. Now let's define the linear functional on this space. So this is basically the Hilbert space. It will be complete norm linear space. So then define the linear functional on this Monarch space or Hilbert space by f of some f. It will be given by my integral with respect to the x square from minus 1 to 1 for all f in L2 of minus 1. Then you have to find the norm of this functional. Means if this is denote the norm of the linear functional, then you have to find the f 5 times norm f square. What will be the value of this? Okay. So this is the NPTEL reference. So you can look at it in order to solve this. Okay, we will use ridge representation theory basically to solve this problem. So what is this saying? Ridge representation theorem. So this is basically characterize all bounded linear functional on a Hilbert space, right? And so basically L2 of over some set, you can take any compact metric space or locally compact. So L2 of that will be a Hilbert space. So basically it's saying that let T be a bounded linear functional on, here I am stating only for L2 of over some set X because I only need this one, but this is true for any in Hilbert space, or more generally this theorem can be true for LP spaces, not necessarily Hilbert spaces. Then there exists a unique G in L2 of X such that T of F is given by integral of F Fx Gx bar, and this is the measure in the X space X. So this we will take the measure space of X. There is a measure for all f in L2 of X, and moreover the norm of this functional will be equal to the norm of this function g. So in the left hand side, this is basically the operator norm, functional norm. This is the operator or functional norm. And the right hand side, this is basically norm, functional norm. So this is L2 of this x, right? Okay, so ridge representation is saying that take any boundary linear functional, it will be given by this integral form, and the operator norm of this functional will be same as the norm of this function g, right? And so this is the L2. I have stated it for only L2 of x, but more generally any Hilbert space there is a notion of inner product. So there you can say that if there is any boundary linear functional, then there is a unique function in again that Hilbert space, it will be given by this, like this inner product T of f, it will be some given by f with some inner product g, and the norm of this T will be the norm of g, right? So it is for Hilbert space. And more generally for LP spaces, this type of theorem is also true, but there then the G will be belongs in some L P dash space, where P dash is the conjugate exponent 1 by P plus 1 by Q. This type of is satisfies. Means if you take f from LP, then G will belongs to in LQ space, and it will be unique, and it will be given by this type of integral formula, and the norm will be again this. So this is more general version for LP. Here I have only stated for L2 only, because I in that solving this I only need for L2. Okay. And what is this? Let me write also the what is this functional norm? Not to recall. So let me. What is this norm of this functional? So this is given by the supremum of all f which is less than equals to 1 times mod of Tf. So this is the functional norm of T, and G is the norm in L2, right? Now here we have the functional is given by this. So this is a functional in L2 of minus 1, 1. Here we have the space is L2 over the set minus 1, 1. So this is again a Hilbert space, and so this is Hilbert space, and again f is in L2 of minus 1, 1. Then the norm of f, how it is L2 norm, it is defined like this: integral from minus 1 to 1 mod of fx squared dx. This is the Lebesgue measure to the power half. So this is the norm here. And how the linear functional is defined? So capital F is a linear functional from L2 of minus 1, 1 with respect to this norm to R. This is because this is a functional. And how it is given? F, it will take any function, it will be given by this integral from minus 1 to 1 fx and x squared. So this is the given for that. Here it is saying that the functional is given by this. Right. So this is a functional on L2 of A. So by ridge representation we know that because here f is a functional, it will be given like this, and it will be given by the integral of some over some function g. So here g is this x square. Then what will be the norm of f? So norm of will be the norm of g. So therefore by ridge representation theorem, norm of f will be norm of this x square, right, in L2 minus 1 comma 1, right. So therefore we have to only find the norm of x square in L2 minus 1 comma 1. So now norm of, what is the norm of x square here? L2 minus 1 comma 1. So this is basically integration from minus 1 to 1 x square and mod this is x square dx to the power half. So this is minus 1 to 1 x to the power 4 dx to the power half. So the integration will be x to the power 5 by 5, integral from minus 1 to 1 to the power half. So if you put the values 1, it will be 2 by 5 and square root, right? So norm of x square we get square root of 2 by 5. So therefore norm of f, which is norm of x square. So functional norm, here this is the norm of x square, which is square root of 2 by 5. So this is the functional norm. Now let's see what we have to find. We have to find the value of 5 times norm of f square. So then five times norm f square, 5 into 2 by 5, so it's 2. So the answer is 2. Then 5 times norm f square, it is the basically 2. Okay. Okay, any doubt or any questions? No. Okay, so we have done the Gate 2023 question number 32 from functional analysis. Now we have one more question, question number 37. Okay, let's see the other video. Okay, so today we'll solve mathematics Gate 2023 question. This is a question from functional analysis. It is question number 37. It is saying that let L2, this is this sequence space, or this is a square summable sequencer. So, and for a sequence in L2, small L2 basically, so the norm is basically take the square sum to the power half. Then two linear operators are defined, S from both the space from L2 to L2 and T is again from L2 to L2. S is defined like this and T is defined by this. Then you have to check, the four options are given. It's saying that S and T are, you have to basically check that this is compact linear operator or not, right? Okay, so in order to solve this problem, this is the NPTEL reference. Okay, so let's start. So let me first give the what is compact linear operator. So let X and Y are two Banach spaces. Means they are basically complete non-linear space. An operator, linear operator, T from X to Y is called compact operator if, means it will take basically the unit ball, if the take T image of this unit ball where B01 is the unit ball, take the closure, this should be compact in Y basically, because it will map to Y. So the closure of the image of the unit ball should be the compact. What is the unit ball? This is basically B. So this is the definition for the compact operator. What is B01? So this is basically all such X in X such that norm of X. So this is norm in the space X less than equals to 1. Right. And as this is a linear operator, so if it is mapped the closed unit ball to the, it will take the any bounded set, right? So basically this is equivalent again. Equivalent definition. What is the equivalent definition? So T is called compact basically not for unit ball, if any bounded set, if image of any bounded, so closure of the image of compact if T of A closure is compact. Where what is A? Where A is any bounded set in X, right? So this is basically in Y. So this is means basically if you take any bounded set, take the image, apply T, and whatever we will get the image, take the closure. If this is compact, then it is called that linear operator is compact operator. Again, there is another equivalent definition. So this is definition 1. So this is same as take any bounded sequence and see what will be the image of that sequence. So the closure should be compact, means if that sequence has a convergent subsequence, then we can say that T is again compact operator. Again saying that, so T is compact if and only for each bounded sequence xn, the sequence T of xn has a convergent subsequence. Right. So we'll call T is a compact if for every bounded sequence xn, so the sequence T xn has a convergent subsequence. So this is a very useful criteria in order to check that an operator is compact or not. So you will use this one. So so this we will use basically. Right. Okay, so two operators are given, S and T. What is S? Here, first let's do it for S. S is an operator from L2. This is a sequence space with this L2 norm to again L2. So it will take a sequence x1, x2, dot dot dot, and how it will map? It is y1, y2, dot dot dot. Where what is yn? Where yn is 0 if n is 1, and it is basically x n minus 1, right? If n is 2. So how it will look like basically? S of x1, x2, dot dot dot. So y1 is always 0. And what is y2? y2 is x1, y3 is x2, right? So it basically shifts one places, right, in the right. So that's why S is called right shift operator. So this is called the right shift operator. So you have to check that this right shift operator is compact or not, right? So we'll use the last characterization. So you have to find a bounded sequence, so that we have to check that this S of that sequence has a convergent subsequence or not. So we'll show that this S is not a compact operator. Claim. So let me claim. S is not compact operator. So means you have to find a bounded sequence so that S of En does not have any convergent subsequence. So what will be the choice of our bounded sequence? So let's take the sequence to be the En. So this is in L2, right? Why? What is En? Ens are basically 0, 0, dot dot dot, 0, 1, 0, dot 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 dot. Where 1 is in the nth place. right? So basically this is from n greater than equals to 1. This is a sequence. So like this u1, it will be 1 0 0 dot dot dot. e2 is 0 1 0 0 0 now, like this. So clearly these are in L2, right? Because only one term is non-zero here. And note that what are the norm of this En? So L2 norm, so this is n greater than 1. What is xn? So only one term is there to the power of, so basically norm is 1 for all n greater than 1, right? So therefore ens are bounded, right? Because all has norm 1. So en for n greater than 1 is a bounded sequence in L2 with respect to this little L2 norm, right? Now we have to apply S on this sequence. So note what will be this S of En? What S does? S basically shift by in the right by 1 place, right? So it will basically, what it will be? So S is basically S of 0 0 0 0 0 0 1 0 0 0 0, right? So it will shift by 1. So here it is nth place, then 0 0 0 0 0, it will be 1, like this. Here it will be n plus 1th place, right? So basically this is En plus 1. So S takes En to En plus 1. So therefore this S of En, you have to check that this for n greater than 1. So this is basically En plus 1. It has a convergent subsequence or not. So we will prove that, therefore we will show that this does not have any convergent subsequence, right? Why? Not. So if not En plus 1 for n greater than 1 does not have any convergent subsequence. Why? Because if it has any convergent subsequence, then that subsequence must be Cauchy, right? Every convergent sequence is Cauchy in Banach spaces. So now, so therefore let's check what is En minus Em in this L2 norm for m not equals to m. So therefore it is basically contain two terms, right? Only plus 1 and mod of minus 1, right, to the power half. So this is basically 1 plus 1 is 2 root 2. So for n not equals to m, note that distance of En and Em is always root 2, right? So for any n not equals to m, it is at distance always root 2, so it cannot goes to 0, right? So therefore En plus 1 for n greater than equals to 1 does not have any convergent subsequence. Right, because if it has a convergent subsequence, that subsequence must be Cauchy. So therefore E that for two different indices, that difference must go to 0. But as we have shown that this is for any different indices, it is always root 2, so it can't go to 0. So therefore S of En cannot have, let me write it here, S of En does not have any convergent subsequence means S is not compact, which implies S is not compact operator. Right. Okay, so for S it is done. Now what is T? T takes to this. For n odd it's 0, n even it's xn. So claim again, so we'll prove again that T is also not compact operator. So claim T is not compact. So what is T? T basically take L2 to this to T of x1, x2 dot dot dot, it will map to y1, y2 dot dot dot, where yn is basically 0 if n is odd, and this is xn if n is even, right? So basically if you will take any sequence, it will send it to, or in odd places it will be 0, and it will be the xn for n error places is even. So in order to show that this is not compact, again we have to find a bounded sequence so that T of that bounded sequence does not have any convergence subsequence. So again as earlier we will take, so let's take that sequence to be, now this time take E2n, we will take only even E2n where ENs are as early, right? 0, 0, 0, dot, 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 1, 0, 0, like this in the nth place. So means E2n, these are 1 in the even places, 2 nth places, right? For n greater than 1. Then what will be T of En? T of E2n T 0, 0, dot, 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 0, 1, 0, 0, dot, dot, dot. So this is basically 2 nth place. How it will map? In the all odd places it will map to 0, and even places here it is all 0, 0, 0, 0. Because 2n is even, it will map again it to 1 because it is xn, and even places other 0. So it will basically map the same. So E2n it will map to E2n for all n, right? So T of E2n it will map to E2n, right? And again what is the norm of E2n? L2 norm, as early this is again norm 1, right? So therefore E2n is a bounded sequence in L2. Now again you can check that. So claim means note that as early again T of E2n for n greater than 2, basically this is the En again, E2n. This does not have any convergence subsequence. Any convergence subsequence. Why? Because this is as earlier reason that for any m not equals to n, or any m not equals to n, norm of E2m minus E2n L2 norm. This is again you will get root 2. So therefore it cannot have any convergence subsequence, right? Because it has then again that will be Cauchy, mean that difference should goes to 0. So which implies T of E2n for n greater than 1 does not have any convergent subsequence. Which implies that T is not compact operator. Yeah. So we have get that S is also not compact operator and T is also not compact operator. So which option is correct here? S is compact operator, first option is false, B is also false, C is also false, so D is correct. Neither S nor T is compact linear operator. So option number D is correct. Okay. Okay. Any doubt or any questions? You have understand what you just see the video. Yeah, which book? Yeah, for functional analysis there are lots of books. You can see Conway, J.B. Conway, and other is Rajendra Bhatia. Yeah, these two are good books. Yeah, there are also other books also, like B.V. Limay is there. But I think it's better if you look into Conway or Bhatia. They have done it. Conway you will find everything. So just look into Conway. Compact operator you will find it. Yeah. And for ridge representation you can look into Rudin real and complex analysis. There. It's a very good book. There you will find it. Yeah, any other questions? Or any doubt from any other questions? You have done the functional analysis course, right? Or you have not done? Yeah, I think then, yeah, it is on the means very last compact operators. No, means represent spectral theorem is done, but compact operators I think in general it done in, yeah, from the, it was done in the some in general course compact operators. Yeah, yeah, there you will find Limai. Yeah, you can see any books. It's good. Just use the different means sometimes not, sometimes try to use the means equivalent definition for compact operators. Here, what I have done means in general, it's hard to show by very very fast definition. So try to use the equivalent definition. So so that remember just the things. Yeah. Yeah, I will upload this live session also, and this video will, yeah, it will be uploaded in the Gate NPTEL portal also. Yeah, any other doubt? Next time I think I will solve questions from topology. Two questions from topology. Yeah, thank you. Yeah, maybe we can stop. Yeah, thank you. Okay, so let's stop.